Last day we learned the rules for parallel and series resistors. A mixed resistor has both. To solve these, the first thing you need to do is figure out which ones are in series, which ones are in parallel, which resistors can I just add together and treat as one uber resistor, which set of resistors do I have to go 1 over plus 1 over plus 1 over. Then simplify to find the total equivalent resistance, R total. Find the total current, because once you have total current, the question's going to fall apart. So to find the total current, you're going to use total current equals total voltage divided by total resistance. But the first thing you've got to be able to do is recognize which ones are in series and which ones are in parallel. I'm going to call this resistor R1, R2, and R3. Which resistors are in parallel with each other? So R2 and R3 are in parallel. I'm using my abbreviation for parallel. If I went 1 over R2 plus 1 over R3, I would have replaced these with a single resistor, and that new resistor would be in series with R1, and I could just add them. R1, R2, R3, R4, R5. Which ones are in series with each other? Emily? No. R1 is not in series because for them to be in series, the same skiers have to go through them. Here, some skiers veered off before they got to R3. So R3, R4, and R5 are in series. But not R1. Now, Emily, I could combine these into one big uber resistor just by adding them up. And then what I would have, you use your imagination, one resistor right here in parallel with R2. I could then combine those by going 1 over R2 plus 1 over new mystery resistor, get a new resistor, and then I would have one resistor in series with R1. This is the hopscotch dance that we're going to be doing. So we would say, for example, if I call this R1, R2, R3, R4, and R5, pause the video. There are two pairs of parallel in this circuit. Which are the first two that are parallel with each other? R2 is parallel with R3, and R4 is parallel with R5. If I wanted to write this as one great big resistor, I would combine those two, 1 over R4 plus 1 over R5 equals reciprocal. I would combine those two, and the new circuit would look like this. The new circuit would have R1, a mystery resistor, and a new mystery resistor. But the nice thing is, Emily, these three are in series. Add, 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 and I've got our total. And once I find our total, I can find I total. You know what? It's easier to do this with some numbers. So let's do this with some numbers here. I'm going to skip this one, and I'm going to jump straight to example 2. It says, find everything. We're going to find all the voltages and all the currents. We could also find the power, because V times I, if we know 2 things, we know 4 things. But I'm just going to find the voltages and the currents. All right. First thing that I always do is label downhill. If you're wanting to make a little list, you could say, step 1, label downhill. Next thing that I always do is I look for current. Preferably total current, but current anywhere always helps. I don't see any currents in the circuit that you have in front of you. Then I look for any resistor with 2 things. I think the dumb joke that I've made is knock, knock. Who's there? I know 4 things, because if I know 2 things, I might be able to pull a current out of that resistor, and current is a good thing. That's the rule that I use the most. Then I ski the voltages. Because sometimes I don't need to rewrite the circuit mathematically. Sometimes, Martin, if I'm clever, I can figure out a mystery voltage or 2, and I can save myself having to rewrite the silly thing. Finally, if I have to, I'll combine resistors and rewrite using I total equals V total over R total. And then once I've done that, repeat, except I've done the labeling already, so I don't need to repeat that. This is the order that I do things in. And Martin, I have yet to find a circuit that I couldn't solve in doing this. Martin, do you see any amps anywhere in example 2? No. If this wasn't here, if that resistor was gone, then I would say, oh, that's 20 volts, knock, knock, I know 2 things. Oh, that's 20 volts, knock, knock, I know 2 things. I wouldn't have to rewrite this, and that's why I said I always ski first. But with that there, I can't use that trick either. I have to rewrite this. So I'm going to call this here R parallel. Where do you show your work? I'm not too fussy, but show me some work. How about right next to here, I'm going to write 1 over R parallel, and that's going to be 1 over 10 plus 1 over 15. I'm going to combine these two because they're in parallel with each other. (10) reciprocal plus 15 reciprocal is R parallel 0.166666666. What have I forgotten to do? 6 ohms. Oh, by the way, how big was this resistor here? How big was this resistor here? I knew the answer is going to be less than 10. It's always less than the smallest resistor in our parallel group. So I'm going to argue then that this circuit can be rewritten as 20 volts, a 4 ohm resistor, and a 6 ohm resistor. You okay with that, Ibrahim? Why is that so nice? Ibrahim, what's R total? Yes. What's V total? Yep. I total is going to be V total over R total, 20 over 10 in your head. Say it again, what? How many amps leaving the battery? How many amps leaving this battery? How many amps going through this 4 ohm resistor? Knock, knock. How many volts do I lose going through this 4 ohm resistor? Now, a good habit for us might be at the top of the page to go V equals I times R, and if should they ask for a power question, power equals V times I. How many volts? You said it. What? Okay. Start here, start to ski. How many volts do I lose here? Say it again. How many volts must I lose here? Gotta be 12. Knock, knock. I know 2 things. How many amps are going through this 10 ohm resistor? Can't be 2 amps. It has to split up right there. I know it's going to be less than 2 amps. How do you figure that out? V equals I times R. Oh, you know what? Ibrahim, current is voltage divided by resistance. 12 divided by 10. This is going to be 1.2 amps. How many volts in the 15 ohm resistor? Brian, there's 2 ways I could get that 12. I could say, look, we split up and met up. If that's 12, that's 12. Or I could ski this outer ski run. 20 minus 8, still 12. How many amps are going through this resistor? There's two ways I can get that. I can go 12 divided by 15. But Brian, put your calculator down. How many amps are flowing in? How many amps went this way? How many amps must have gone that way? I'll bet you when you went 12 divided by 15, did you get 0.8 on your calculator? And it's nice because now we've got a bunch of ways to get the same answer and check our work. Oh, I could also now go V times I and find how many watts, V times I and find how many watts, V times I and find how many watts. That's now a trivial calculation. You'll notice, Chantel, I didn't draw a complete diagram. I actually never drew R total. From that, once I had everything in series, I could do R total in my head. You can redraw it if you really want to, but I don't bother. But you'll also notice I tried to make this look a little bit like this one. I put the 6 here so I knew that this was 6 ohms. By the way, the other thing I could have done, pause the video for a second. The other thing I could have done, if you look up, how many amps leaving this, Ibrahim? Which means this is 2 amps, this is 8 volts. Does that match what you wrote up there? This is 2 amps, this is 12 volts. Does that match what we said right here? So you can actually do your voltages on the simplified circuit and just transfer them over if you want to. I flip-flop. I'm lazy, whichever method is more convenient at the time. Example 3. This is a little closer to the level of difficulty I'm going to expect you to handle. Find all the voltages and currents, draw a summary diagram. In other words, solve. Now, what would I ask you on a test question? Probably I would say something like how many watts going through the 5 ohm resistor, or how many watts going through the 6 ohm resistor, which would require you to find everything and then go power equals V times I. Step 1, label downhill. Step 2, find currents. Don't see any. Step 3, ski. Not going to help me. If this resistor wasn't here, if that didn't exist at all, then if I skied, this would be 30 volts, knock, knock. It's 6 amps. The question falls apart. I can do a lot with that already, probably. But sadly, okay, we have to rewrite this. The most common mistake that kids do is they say, oh, Mr. Dueck, these are in parallel. Don't write this down. And they go 1 over R parallel is 1 over 5 plus 1 over 12 plus 1 over 6. Don't write that down. Plus 1 over 2. That's not correct because the 12 is not in parallel with the 5. The 6 is not in parallel with the 5. The 2 is not in parallel with the 5. These 3 are in a different relationship. These 3 are in, I'm looking for a word that starts with the letter S. I'm going to argue that this circuit here is the same as a 30 volt battery, a 6 ohm resistor here, a 5 ohm resistor there, but this branch can be replaced with one big resistor. How big? You might be able to do the math in your head. And do you notice, for what it's worth, you all stay on this page? We just turned it into this circuit. One resistor, one resistor, one resistor. So now what are we going to do? We're going to combine these two. 1 over R parallel is going to be 1 over 5 plus 1 over 20. Four? They won't always work out this nice. If you get a yucky answer, don't freak. That's going to happen fairly often. But 4? So what can these two be replaced with? A single resistor. How big? I could redraw this whole thing, but this is my rough sketch. Yes? Okay. You can redraw it, Hannah, if you want to. I'm lazy, but organized. Hannah, what's our total? Yep. I total is going to be V total over R total. It's going to be 30 over 10. Hannah, in your head. So 3 amps going through this 6, 3 amps going through this 6. Knock, knock. I know two things. Darwin, how many volts in this upper resistor here, in the 6 ohm resistor? What's our voltage loss? Yep. By the way, a good habit maybe on each of these questions is just to write V equals I times R somewhere. 18 volts. Okay. Here, there's 3 ski hills. I don't know how big they are, but I can tell you how many volts I lose going down this ski hill. How many volts must I lose going down this ski hill? How many amps are going through that ski hill? I know two things. I can find it. V over R, yes? 12 divided by 5. 2.4 amps went that way. How many amps must have gone this way then? Knock, knock. I know two things. How many volts? 12 times 0.6, 7.2? Double check me. How many amps going through this right-hand 6 ohm resistor? Still 0.6 amps. How many volts? I think 3.6. How many amps going through this 2 ohm resistor? Still 0.6 amps. How many volts? 1.2 volts. Do a quick check. Make sure that 7.2 plus 3.6 plus 1.2 adds to 12. It should. It has to. Does it? That can't be a fluke then. It said find all voltages and currents. We're done. Here you go. All I can really do is give you a few more junctions, Chantal, a few more wires. I can't really say I'm going to make it tougher. I'll say I'll make it a little longer, but not tougher. Here is a good example of a using principles of physics right to explain question. What happens to the total current as measured by the ammeter when the switch is closed? No change, increases, or decreases? I think it's going to change. My gut right now is A is wrong. Okay. You know what? Open. Closed. While it's open, no current can flow through that branch. We can ignore it totally. What can you tell me about this 20 and this 5? They are in, I'm looking for it, begins letter S. So boys and girls, what's R total when it's open in your head? What's I total? Well, that's going to be V total divided by R total. I'll bet you can do that in your head as well. It's going to be 100 volts divided by 25. 4 amps. Now, when we add a resistor, that's like opening up an extra ski run. Sorry, when we add a resistor in parallel, that's like opening up an extra ski run. There's another path for skiers to go through. Do you think that means we can fit more skiers or less skiers? I think more. I think current's going to go up. Also because this will be using more power. It would be needing its own set of charges. I think I total is going to go up is my gut. Let's find out. Closed. Now these two are in. So I'd have to go 1 over, I'll change colors just to make it a bit more obvious. 1 over R parallel would be 1 over 5 plus 1 over 10 reciprocal. What can I replace that 5 and that 10 with? $3.33333333333. So how big is the total resistance now? This can be replaced with a single resistor of 3.333. So I'm just kind of imagining it right there. This is 20. I think our total is 23.33333333. And I'm going to, on my calculator, use my answer button and just go plus 20. And now I've got 20.3 repeating. I total is going to be 100 divided by 20, sorry, not 20 point, 23.3 repeating. I'm going to use my answer button. .3 amps. So what's the answer, A, B, or C? Evan? So B. And for your proof, I would just, there, I solved it. I want you to notice a few things. When you add a resistor in parallel, even though you're adding a resistor, because you're adding it in parallel, hang on, we're going to pause. Where was I? Oh. When you add a resistor in parallel, even though you're adding a resistor, when you add a resistor in parallel, what happens to your total resistance? Bigger, smaller, or stays the same? Smaller. This is a little counterintuitive. When you add a resistor, Mr. Dueck, why doesn't resistor go up? It does go up if you add it in series, but if you add a resistor in parallel, our total goes down. Oh, and if our total goes down, I total must go up because our total's on the bottom. You know what? If you add a resistor in parallel, it's as though at a congestion point on your ski run, you opened up another path for people to go, you can get more skiers going. And because it's easier for them to travel, you have lowered total resistance. A good question for this that I might also ask is, what happens to the brightness of this bulb when you close the switch? Brighter, smaller, or stays the same? This is where I would use power equals I squared R, because I don't know the voltage drop through there, but I know the current through there when it's open. It would be 4 squared times 20. It's a 320 watt bulb. When it's closed, it would be 4.28571 squared times 20. Strangely, when you add an extra bulb in parallel, this one gets brighter. What about this bulb? Well, originally it was 4 squared times 5, 80. When you close the switch, you have 4.3. I can't assume that 4.3 amps goes there. In fact, it's going to be splitting up the current. It's going to have much less than 4 amps. It's going to be dimmer. So closing the switch, this bulb would get dimmer. This one would turn on. This one would get brighter. Not immediately intuitive, but if you run the numbers, that must be the case. What's your homework? Number 1? 2 is good. 3 is good. 4 is good. Number 4, you don't know which direction the current is going. It doesn't matter, but if you want to assume the current is going to the right, that's fine. You'll get the same answer if you assume the current is going to the left, because you're just finding the total resistance anyways. 5 is strangely drawn. I'm going to assign 5 because I would never draw it that way with the battery in the middle. I would draw it a different way, but see if you can figure it out. 6 wants you to find the battery. Psst, I would start right there because I know 2 things. 7 is really cool. The key for number 7, they told you that 3 amps goes through the 6 ohm resistor, so you know that this is 3 amps. That's where I would start. 8 is good. We'll skip 9. You have 25 minutes, almost a half an hour actually,